Woo, here we go. Okay, so we're gonna wrap up thinking about the chemistry of air. Um, just a quick refresh on our recollection. We have the five most abundant gases that are in our atmosphere. So the most abundant gas in the Earth's atmosphere is nitrogen. It was identified in 1772 by a Scottish botanist. It's important that we know that atmospheric nitrogen is relatively unreactive, but it's sometimes used to replace air in packaged foods to preserve freshness, and it's present in our atmosphere in 77%. Then the next step is oxygen. This is the second most abundant gas that's present in our atmosphere. While it's the most abundant element by mass in our Earth's crust and in the ocean and in the human body, it's actually only present in 20% as the component in our atmosphere. Then we have water vapor. And water vapor we know is really special. So, as a gas, it's invisible, but it's also the only compound that exists naturally in solid, liquid, and gaseous phases in our atmosphere. Then we've got argon, which is present in 1%. So this is an unreactive or inert noble gas. And there are other inert gases that are present in much smaller percentages, but maybe the place where we are most familiar with noble gases is a neon sign. So argon is actually what's responsible for producing the blue color that you see there. And then carbon dioxide is present as 0.04%. So one of the things that's really important as a distinction here is that we talked about how water vapor and argon are the third and fourth most abundant gases in the atmosphere. But if we think about the 2% water vapor concentration that was listed, right, it can actually vary from 0 all the way to as high as 4%. And so water vapor is in many places the third most abundant gas in the air. But in a really dry place like Tucson, where it's super dry most of the year, then argon is in the third position and water vapor is in the fourth. And the last piece that is important for us to acknowledge is that water vapor and carbon dioxide are greenhouse gases. So when you're thinking about water in the atmosphere, you might be thinking about some of the roles that water has played. So the last 2 weeks, we've been thinking about the formation of clouds, storms, and precipitation. And we know that meteorologists are interested in knowing and keeping track of how much water vapor is in the air. And so one of the variables that they use is dew point temperature. So what do you see when you look at this table? What stands out to you?
It's pretty constant and it's increasing for both sides.
Yeah, right. So as dew point temperature increases, the amount of water vapor concentration also increases. And so the trend that has been generally identified is for every 20-degree Fahrenheit increase, the amount of water vapor in the air roughly doubles. Now, I don't know about you, but when I look at a dew point temperature of 85 and 4% water vapor concentration, I think about really humid places, right? Like Florida or Louisiana. And, right, there are world records for these. So, the low 90s is the highest dew point temperature that's been observed in the United States. So that's 32 degrees Celsius. But that's a very warm and very humid day. So we should talk about wet bulb. So this is where air temperature is always going to be equal or warmer than the dew point temperature. So experiencing an 80-degree Fahrenheit or 27 degrees Celsius dew point is very unpleasant. So it's not just the temperature, it's the temperature plus the moisture. And, right, it's possibly life-threatening because your body might not be able to cool itself. I bet you can think about scenarios where, right, if, say, for example, someone was practicing a sport and they were experiencing, right, a really high dew point, that could be dangerous. So if the air temperature is in the 90s or even warmer, right, there's this risk of heat stroke or potentially death because of the inability to cool itself. So you might have read or seen examples, say, for example, of students in the summer practicing for football or for soccer, and how they actually have to take measurements to make sure that there is shade or breaks where they can get water, anything that helps the body cool itself, because those dew points actually can be life-threatening if they're high enough. Okay, so take a look at this visualization. and think about what it's trying to show. So we know that relative humidity is a percentage of how much moisture is in the air. And we also know that there's a maximum that the air can hold, right? So if we think of the air as a container, there's a maximum value of water that the air can hold. And so dew point is the absolute measure of how much moisture is in the air. So if we have a temperature and we have our relative humidity, then we can calculate what our dew point is. So if we have a temperature of 35 degrees Fahrenheit and a relative humidity of 50%, then our dew point would be 18 degrees Fahrenheit. Likewise, if our temperature, say for example, was 95 degrees Fahrenheit and our relative humidity was 50%, our dew point would be 74 degrees Fahrenheit. So you can see how the dew point increases over time as the temperature increases, but in this case, our relative humidity stays the same. Well, what if our relative humidity increased? Well, then our dew point would increase even further. So we've looked at how to do those calculations. I've got an example that we'll take a look at. Today, we're going to think about calculating partial pressure. So the partial pressure of water vapor is the total portion of total air, is the portion of total air pressure that's exerted by our water vapor molecules in a given volume of air. So a good way to think about this is it represents the pressure that water vapor would exert if it was the only gas that was present. So this pressure is always going to be temperature dependent, and it's going to increase as our temperature rises. And it's really important. It plays a crucial role when we're determining humidity. So as we think about things like calculating dew point or calculating partial pressure, these are all ways that we can measure how much water vapor is present in our atmosphere. So a quick refresher of your recollection, the ideal gas law. So it's a formula that describes the relationship between pressure, volume, temperature, and the number of moles of an ideal gas. P in this case is our pressure, V is our volume, N is the number of moles, R is the ideal gas constant, and T is temperature. One of the pieces that's really important for us to be savvy about for this equation and others is the units that we're using. So we always want to make sure that when we are given information, that our units within our calculation don't need to be converted to a different unit in order for us to do that calculation. Okay, so for Dalton's partial pressure, we're going to rearrange this equation, and we're going to show that the pressure of the gas is going to be proportional to the amount of the gas. So the most important piece here for us to pay attention to is the following. So pressure, can you think of some units that we use to measure pressure? What are some of the units we use to measure pressure?
ATM.
Yeah, ATM is a great example. We also have our millimeters of mercury. We have torr. We have PSI. All of those are examples of units where you could measure pressure, or kilopascals, kPa. All of those are examples of, right, units that are associated with pressure. And then N, of course, is our amount of the gas, right? That's the amount in moles. And it's useful for us to remember, right, when we're calculating moles, if we know the mass of our gas and we know its molar mass, we can calculate the amount of moles. Okay, so we've rearranged our equation for pressure. Now the next piece that we're going to be thinking about that is super relevant to this is the following. So we can use that RT over V factor to be able to convert the amount of a substance to the pressure that's in the container. So R is our gas constant. So let's take a moment and annotate this because it's going to be helpful for us. So here's R. Notice the units here are atmosphere times moles. Oh, sorry, liters times atmosphere per mole K. So, right, that means that we have ATM in our numerator, we have liters in our numerator, and then we have moles and our temperature in Kelvin in the denominator. So this is R. And then, right, our temperature we have here, and that's in Kelvin. So we're paying attention, right? Our units for temperature are Kelvin. Notice how the units for Kelvin are in the numerator. The units for Kelvin with the R constant are in the denominator, so these cancel. And then our liters here, right? That's for volume. That's going to cancel. And right, so volume, and that's liters. And then we have moles over here. That's the amount of the substance that we have. That's going to be our N. So notice we have RT over V. That's this part. Helpful for us to identify. So here's our R. Here's our T part of the equation. And here's our V part of the equation. Right? And then our moles are measured in N. So we can calculate if, say, for example, we had a 0.01 mole of gas in a 250 milliliter container. Notice I needed to convert that from milliliters to liters. So that's an important conversion for me to pay attention to. So I have to convert that to liters. And my temperature, ooh, let me fix the, sorry, that's volume. So that should have been blue. So this needs to be converted to liters. And then my temperature needs to be converted from degrees Celsius to Kelvin as a conversion, right? So there's at least 2 conversions that I need to do here, and then I can calculate my pressure. Once I substitute and solve, right, I'm able to identify my pressure as 1 atmosphere. But notice I had to do those 2 conversions first in order, right, to be able to calculate the correct pressure, which in this case is atmospheres. How do I know that it's atmospheres? Well, the atmospheres is actually present in the R constant. So I want to make sure that my atmospheres matches my R constant. There are many R constants out there in the world. Not all of them have atmospheres. So it's really important for us to pay attention, make sure that our units match when we're doing this calculation, and to make sure that we're doing the correct conversion. Okay, so we do all of that calculation. What's our next step? Well, let's think about this. So let's say, right, we had the same size container, still 250 milliliters, but now it's 0.004 moles of hydrogen gas, right, at the same temperature. So if we think about our H2 gas compared to what we were looking at earlier, so here's our H2, right? This is an example of a diatomic gas, right? We're still substituting in the same. So this is still our R. That's super useful. This is our T. Our temperature hasn't changed. The only thing that is changing is the amount of our moles. So our volume stays the same, right? It's still in liters. The only thing that has changed is the amount of our moles. So if you're thinking about, right, that calculation now, right, hydrogen gas is only 0.4 atmospheres. So that's going to have less pressure than the previous example. And again, we know that that's correct. Why? Because our units here for atmosphere matches our units, right, for the pressure of our hydrogen gas. Okay, so we've done that thinking. Let's do one more example. Make sure that you're comfortable doing this on your own. So this is if we had 0.006 moles of nitrogen gas in the container. So similar to what we were thinking about, nitrogen is a diatomic gas, except now there are 3 bonds between the nitrogen, and there's a lone pair on each nitrogen atom. That's our Lewis structure. Again, if we're thinking about this, this is our R constant. This is our temperature. And this is our volume. And now we're looking at 0.006 moles. So this would be 0.6 atmospheres, again, of nitrogen in the container. So why does that matter? Why is that important? Well, what if we had all of those present in our atmosphere, which we do? So how would we take into account? Well, we'd have to take into account our hydrogen and our nitrogen, and we would add those two together, and that would be our total pressure of one atmosphere. So if we think about, right, then the pressure of the atmosphere, it's going to be made up of partial pressures of each of the gases that are present. And so that's why we need to think about how to calculate partial pressure. So let's think about this. Partial pressure is the total pressure that's exerted by a wet gas is equal to the sum of the partial pressure of the gas plus the vapor pressure of water that's at that temperature. So if, say, for example, we were to take a gas, any gas, and bubble it through water, it's going to contain some water molecules, right, even after it's bubbled through the water. And so that's why we say that it's wet. So the total pressure of this wet gas is the sum of the partial pressure of the gas itself and the partial pressure of the water vapor that it contains. And so the latter partial pressure is called the vapor pressure of water. So you can always do a calculation, and most things are going to have at least some amount of water. You'd have to do a treatment in order to make something anhydrous. Okay, so here's an example, right? We have our temperature in degrees Celsius. We have our vapor pressure in millimeters mercury, as well as vapor pressure in kilopascals. So this is a table for your reference. Let's go ahead and calculate and think about how we would solve this problem. So we've got 0.321 grams of zinc metal that reacts with hydrochloric acid. So the first thing that we're going to need to do is generate a balanced equation. So we've got our zinc metal. That's going to be a solid. That's going to react with our HCl, which is going to be a gas. And, right, it's collected over water. So we are not sure yet what the products are going to be, but we can think about that, especially, right, as, right, we continue to solve the problem. So we have the resulting hydrogen gas, so that's going to be H2, some type of gas, which is the product, is going to be, right, so we also have zinc, that's probably going to be an aqueous ion. And we have chloride, that's also probably going to be an aqueous ion. And then we're going to think about how we balance that equation. So what are the coefficients that are necessary in order to balance this equation? Well, I've got two hydrogens here, so that's going to be a 1. I need to put 2 here then, because I need 2 hydrogens, which means I'm going to need 2 here. And then each of these can be 1. So that's my balanced equation. That's the first place that I start. I have my barometric pressure. That's 754 millimeters of mercury. So in order to do this, I'm going to need to calculate the moles. So that's going to be in green, the moles of my zinc metal. So I'm going to need to know the molar mass. Of zinc in order to get to my moles. And then I'm going to use my pressure, which in this case is my 745.4 millimeters of mercury. So I have everything that I need in the problem. I had to create a balanced equation. Now let's go ahead and take that balanced equation and do some calculations. So the first thing that we're going to do, now that we have our balanced equation, is we're going to think about our actual calculation. So our total pressure minus the pressure of water, right, is going to be the pressure of the hydrogen gas. So that's something that I'm going to need in order to be able to calculate this problem. So they gave me the 754 millimeters of mercury. I could use the table to look up the 23.8 millimeters of mercury at the temperature that was given. So if I subtract the amount of water pressure from the total pressure, I'm going to be left with the pressure of my hydrogen gas. Now, this is in millimeters mercury. I need to do a conversion. I'm going to convert my millimeters mercury to atmospheres. So my conversion in this case is just going to take, right, the information that I am given or that I can find in the table and convert it to a usable unit. The reason that's going to matter, right, is because I'm going to take, right, the value that was given in terms of the mass and convert it to moles. Once I know the amount of moles from my balanced equation, I can find the relative ratio. So for every 1 mole of H2 gas, right, there are 2 moles of zinc, right? Let's look. Oh, that's because, right, it's a half. Right, so for every one of this, I have a half of zinc, so that's why I can do that conversion, right? Think about my H2, think about the fact that I only have 1, so I need 2 moles of zinc for every 1 mole of H2. Then, right, this value is my R constant, so this is my 0.0820 liter atmosphere per mole Kelvin, and then, right, I can convert to find my Kelvin, and I can find my pressure. So once I plug in all of that information with the correct amount of my atmospheres, right, then I can do a calculation that gets me to the volume of my H2 gas. So notice the kind of pattern that we followed here. We had a balanced equation. We solved for a partial pressure. We converted that partial pressure to a unit of pressure that we could use, right? And then we substituted and solved. So this is an example of a layered problem-solving process, but one that takes advantage of your knowledge of partial pressures. Okay, let's look at another example, and this one's going to be really helpful for us because we think about carbon dioxide all the time. So here's the challenge. Carbon dioxide hydrolyzes in water to form aqueous carbon dioxide. So there's some equilibria that are associated with this hydrolyzation. So there's equilibria that are associated with the carbon dioxide gas, the bicarbonate ion, and the carbonate ion. And notice, right, they're equilibrium constants based on the concentration of those for each. Okay, so if we know that, what do we do? So the first thing we need to do is kind of establish some of our assumptions. So the autoionization for water is 1.82 times 10 to the negative 16th at 298 Kelvin. And we know that the concentration of water isn't changing, so it's so much larger than the concentration of the ions. So we can think of our water as essentially constant. This is the reason why you don't include water or the concentration of water in your equilibria calculations. So essentially it's 1, or unity. So we multiply our concentration of water to get the ion product. So that's just our Kw. And so then, right, we have 1.0 times 10 to the negative 14th at 298 K. So in pure water, our H plus is going to be equal to our OH minus. And you know this when we think about pH, right? So pH we could define as the negative log base 10 of our hydrogen ions concentration, which, right, at 298 Kelvin is going to be 7.0. That's neutral, right? When the pH is less than 7, then our solution is acidic. When the pH is greater than 7, then our solution is going to be basic. So that's going to be super useful for us as we do this calculation. Okay, so now that we've got our equations, we can set up our equilibria and solve using simultaneous equations. So essentially, we're going to substitute for one and solve for another. So if you take a look here, right, we have our equilibrium constant initially. This is just for our carbon dioxide. And that's just going to be our wet carbon dioxide over the partial pressure of carbon dioxide. For our next equilibrium constant, it's going to be our hydrogen ion concentration, our bicarbonate ion concentration over wet carbon dioxide. And then our equilibrium constant for our carbonate is similar. It's going to be our hydrogen ion concentration, our carbonate ion, and then over our bicarbonate. So each of those we can then rearrange and substitute and solve. So if we want to get all of these things in terms of what we can actually measure, we can rearrange them. So we can measure, right, our partial pressures, and that allows us to calculate our concentrations. That's really what this is showing. So we want to get all of these things in terms of something we can actually measure. And then there are several quantities that we might be interested in. So like the total dissolved carbon, for example, might be something that we could rearrange and calculate and solve for. Here's the really cool part about atmospheric chemistry. So more carbon is dissolved than we would expect from just Henry's law alone. So we can determine an effective Henry's law constant, which is going to be greater than the actual Henry law constant. And that's again because of those equilibrium expressions, the fact that carbon is going to move from CO2 to HCO3 to CO3 minus. Our carbon, right, can transfer. It doesn't ever get created or destroyed, but it can transfer to another form. So this figure is going to show us a couple of things. So it shows us that the effective Henry's law constant is greater than the actual Henry's law constant, and that the difference, right, is because of the carbon that dissolves in forms other than wet carbon dioxide. And these forms are going to be in equilibrium with our gaseous or our gas phase carbon dioxide. So if you take a look at the axes of this figure, right, our y-axis, right, is a measurement per pressure. Our x-axis is a measurement per pH. And then we can think about our concentration of our carbon dioxide. And so this figure allows us to think about the relationship between pH, right, and CO2. So our effective Henry's law constant is dependent upon pH through the hydronium ion concentration, and we can actually see that in this figure. So the total amount of dissolved carbon then is a strong function or relationship to pH, or the hydrogen ion concentrations. So the effective Henry's law constant then for a pH of 8 is going to be 10,000 times larger than the Henry's law constant for CO2 that we could calculate. So why does this matter? Well, if we're thinking about the aqueous chemistry of carbon dioxide, we have to think about actual ion concentrations. So let's assume that our solution started out neutral and that the total positive ions exactly balance the total number of negative ions. So that means, right, our H plus ions has to be equal to the concentration of our hydroxide ions, bicarbonate ions, and carbonate ions combined. Then if we can do that, then we can use our equilibrium relationships that we just derived, and we can rewrite our expression, substituting in our equilibrium coefficients, the Henry's law constant, and the partial pressure of CO2. And you're like, oh my goodness, that's a lot of calculation. It is, but here's the really cool part about doing that calculation. For a temperature of 298 Kelvin and a carbon dioxide mixing ratio, right, of 350 ppm V, then the pH of the solution of water and the dissolved carbon dioxide is going to be 5.6. So here's the really cool part. Because atmospheric CO2 is always there, when we think about rainwater, if it's pure, the only thing that's in it is water and, right, CO2 or other atmospheric components, then rainwater is always going to have a pH of 5.6. So you might be thinking to yourself, well, wait a minute, Sloan, why do we do all of those calculations? Well, because if you change the components, say, for example, you change the components that are in the atmosphere, then you can change the pH of the atmosphere, which means you could change the pH of the rainwater. The reason why that's such a valuable calculation for us to be able to do is because, right, if you think, say, for example, about seeding clouds, right, maybe you're going to add sulfuric acid into the atmosphere to seed a cloud. Well, that's going to change the pH of, say, for example, your rainwater. So these are calculations that are necessary for us to think about as we think about the aqueous chemistry of the atmosphere. All right. We are coming up quickly on our last class, so I want to talk just a little bit about your community water projects. We're going to check out an exemplar, and then I want to make sure there's time if folks have questions. So give me just a moment to switch to that. So let me pause, stop the recording.